Hello and welcome to Lecture 2 for Introduction to Astronomy. I am your professor, Michael Jaramillo, and let's begin. So the learning objectives for today's lecture will be on the geometry of the celestial sphere, how planets move in the celestial sphere, how the various models of our solar systems work and how they were conceived. We will also hear about the theories of Nicholas Copernicus and the Copernican revolution, specifically how we went from a geocentric model to a heliocentric model. And then we'll also discover or just talk about the birth of modern astronomy and Galileo's many notable discoveries. Galileo was a pretty cool guy. He stood up for scientific inquiry in the face of religious persecution, and I think that's really, really cool. We also go over the observational consequences of the heliocentric model because the heliocentric model means that we will have some events that occur pretty rarely, like solar and lunar eclipses. Astronomy is one of humanity's earliest activities, and it was very important for our ancestors because it allowed them to predict daily events and annual events from the night sky, which was crucial for their survival because it let them predict the coming of the seasons and sometimes when there would be rains or when it was best to harvest. But the successes of their predictions with their early astronomical models got to their heads, and so they began to develop some religious ideas around the night sky. And we know that their early models of the universe sometimes could provide some accurate predictions, but it also often incorporated many unscientific methods, and it would invoke religious ideas or beings, supernatural beings that are unscientific. But it's very useful for us to understand how they made these uh, logical leaps and how they came up with their ideas because it lets us understand the progression of astronomy throughout history. I want to introduce this concept of the celestial sphere. So, early astronomers imagined that the Earth was surrounded by a very large sphere and that the constellations and the stars were painted on that sphere. And then that celestial sphere rotated around the Earth, and that's what gave rise to the motions of the night sky. And so this analogy isn't quite accurate, but it's still useful for understanding how to observe things on the night sky. We know that they're not objects painted on a magical huge sphere, but are instead stars and planets that are dispersed throughout the universe around us. So the celestial sphere is divided into northern and southern hemispheres across its celestial equator, much like our Earth has northern and southern hemispheres, which is divided by an equator. And at the top of the celestial hemispheres are the north and south celestial poles, with the North Pole having a star directly overhead known as the North Star, which we also call Polaris. Polaris's scientific name is Alpha Ursae Minoris because it is the first magnitude star in the constellation Ursa Minor. So because it is the first magnitude, meaning it is the brightest star in that constellation, it has the designation Alpha, and then the Ursa Minoris is just the name for the constellation. So that star is the brightest star in Ursa Minor. So as ancient astronomers were observing the night sky and getting familiar with all of the objects in it, they found that almost all of the celestial objects moved uniformly eastward across the celestial sphere. But there were five stars, I say stars in quotes, that seemed to wander around, meaning that they would occasionally move in the opposite direction. These wanderers were better known as planets, which is derived from the Greek word for wanderer. And these were the planets Mercury, Venus, Mars, Jupiter, and Saturn. And so they would occasionally exhibit some weird types of motion. And we call that motion prograde and retrograde motion. And now this is motion relative to the observer. So this is just, it appears to us observing on Earth occasionally that objects seem to move backwards westward in the celestial sphere as opposed to the common eastward ones. So the objects that move in the normal direction in the east with all of the other stars, those have prograde motion. And then retrograde motion is when you move against that uniform motion towards the east and you go backwards and you go westwards on the celestial sphere. And so, as astronomers observed these wanderers more, they realized that not only the position, but the brightness was also correlated with when these objects would experience their prograde and retrograde motion. Sometimes the objects would be brighter or dimmer during their moments of prograde and retrograde motion. But why? So, in attempts to explain the prograde and retrograde motion that early astronomers saw, led to this idea of the geocentric model in the early Greek era. This geocentric model was really favored partially because it seems nice and elegant. Having the Earth at the center of the universe makes us feel really big and important. But it couldn't really provide very many accurate predictions. In fact, in order to get the geocentric model to explain a lot of the phenomenon that they saw in the night sky, they had to keep making it a little bit more convoluted. They needed two types of circular motion. You would need to have an object, to have it go retrograde in the sky, it would be orbiting around you in a circular path, but on that circular path that it's orbiting, it would be in another circle. So this second circle is called the epicycle, and it describes the small circular motion about the central point of the moving body that we're talking about going around the Earth. But despite the increased complexity that this model required, eventually they fully fleshed it out to the full Ptolemaic model by 140 AD, and it was very convoluted. There were more than 80 independent circular paths that were needed to describe just the motion of those five planets and the Earth and Sun and Moon. So, despite being extremely convoluted and being complex, and also having some inconsistencies and not being able to predict everything accurately, the Ptolemaic model lasted for almost 14 centuries. But by the 16th century AD, the early Aristarchus philosophy was rediscovered by a scientist by the name of Nicholas Copernicus. This philosophy was focused on a sun-centered universe or a sun-centered solar system model and what we call the heliocentric model. And this period of the rediscovery by Copernicus of the heliocentric model is called the Copernican Revolution. This is a scientific realignment with the idea that the Earth is not the center of the universe. They used scientific principles and the scientific method to come up with their ideas and hypotheses, which they were then able to test and retest. This was a fully scientific revolution. But despite its simplicity and its ability to make accurate predictions with a much simpler model that didn't require 80 epicycles, it wasn't widely accepted because the religious ideas at the time backed this idea that the Earth was the center of the universe. It made sense to religious scholars that the Earth should be the center of the universe. But by 1616, other scientists like Galileo Galilei popularized Copernicus's ideas, and he even had to stand up against the Catholic Church, but Galileo did, and he really helped solidify the heliocentric model in the public's mind. Copernicus and his revolutionary idea of popularizing the heliocentric model had seven main points that distinguished it from the geocentric model of the Ptolemaic model. And these are that these celestial spheres, aka the stars, do not have one common center. The Earth is not the center of the universe, but is instead just the center of gravity for the moon's orbit. All of the wanderers that are the planets revolve around the sun. Also, that the distance between the Earth and the sun is very small compared to the distance between the sun and the other stars in the night sky. They use the word firmament here because this was the idea that there was still potentially like a sphere out there that these distant stars were a part of, but this was starting to lose popular belief. The firmament started to dissolve, and we started to think of it as individual distant stars rather than a painting of stars above us. And so this motion of the firmament was not the motion of the firmament itself, but rather the motion of the Earth, which rotates about its fixed poles. Also, the motion of the sun is not due to the sun, but rather the motion of the Earth. And so then what appears as retrograde and prograde motion of the planets is not actually the planets moving, but rather effects that we see from the Earth's rotation when we look out. Now that we've established the heliocentric view of the solar system, let's revisit those wanderers, those planets that exhibited those weird motions of retrograde and prograde motion. With this idea of the heliocentric model in our mind, we can categorize the planets into two groups. The inferior planets, that is the ones that are closer to the sun, these are Mercury and Venus, and the superior planets, that are the ones whose orbits are further than Earth's, that are Mars, Jupiter, and Saturn. And so these inferior and superior planets can be observed either in conjunction, that is when they're closely approaching the sun, or in opposition when they are opposite the sun, because the sun is in the center of our solar system. And so explaining the motion, the prograde and retrograde motion of the planets can be done with the heliocentric model. Inferior planets never stray too far away from the sun. They are always closer to the sun in their orbits than the Earth. And this results in two periods of conjunction. Inferior conjunction, which causes them to appear to move in retrograde, and superior conjunction, which makes them appear to move in prograde motion from the Earth. And then superior planets are not as tied to the sun's ecliptic as the interior, so their orbits are a little bit more different, and so they can exhibit periods of prograde conjunction and retrograde opposition. And superior planets are brightest at opposition when they're closest to the Earth. That makes sense. And inferior planets are brightest just before or after conjunction. That is when they are experiencing the maximal reflection of the sun's light to Earth. So we've been talking about ancient astronomy and we've been getting closer to modern times, but we can really think of the birth of modern astronomy as when Galileo Galilei first turned his telescope up to the night sky and started making scientific observations. So after he heard of the discovery by Hans Lippershey of the telescope, Galileo developed his own handheld ones that could magnify objects to 3 times to 9 times their normal size. But he reckoned that in order to observe the things in the heavens much more closely, he needed a larger, higher magnifying telescope. So he worked and he developed his own telescopes that could eventually magnify objects up to 30 times. So using his fancy new telescopes, he looked up at the night sky and discovered many new objects in our solar system, such as the moons of Jupiter, which are called the Galilean moons. Well, that is the first 4 that he discovered, and they are the largest, and they are referred to as the Galilean moons. And when he observed these smaller moons orbiting around Jupiter over the course of several weeks, it helped him really feel confident in the necessity for Copernicus's heliocentric model. He could see with his observations that small things do orbit around larger things. Galileo made a lot of notable discoveries with his telescope. That is the same telescope pictured below. It does not look quite as fancy or as large as our modern telescopes, and yet he was still able to make massive, groundbreaking discoveries with it. So, some of these discoveries include he was able to resolve individual stars from that glow of the Milky Way in the sky. At the time, with just the human eyes, the glow of the Milky Way was just a diffuse white hue in the sky. But by looking at it with a telescope, he saw that that glow was due to hundreds and thousands of stars concentrated in the band of the Milky Way. He also made the first spots, or he also made the first observation of moving spots on the sun's surface, which we now know as sunspots. This confirmed that the sun rotated about an axis. He also made the first observations of craters, mountains, and valleys on the moon. This really suggested that the moon is a lot like the Earth and that it is made up of rocky stuff. Most important, which I mentioned on the last slide, is that Galileo discovered 4 moons of Jupiter with periods of about 2 to 17 days in their orbit around Jupiter. This directly contradicted the Ptolemaic model, which relied on orbital bodies to be stationary. He also made the first observations of the phases of Venus, which allowed for the he also made the first observations of the phases of Venus, which were allowed in the Ptolemaic model, but he discovered that the phases were completely unaligned with the Ptolemaic predictions. So something wasn't right with the Ptolemaic model. And Galileo was going to tell everyone about it. He was going to tell everyone that the heliocentric model could explain all of his discoveries, but the Catholic Church got pretty mad at him for that. They charged him with heresy, they sentenced him to house arrest, and they banned all of his works until 1836. However, the Catholic Church was not as dominant across all of Europe. It was strongest in Italy, where Galileo was, but in places where it couldn't reach as far, Galileo's ideas were able to spread, and people were able to build on his ideas and continue discovering. So now that we understand the origin and background of the heliocentric model, let's talk about some of the things that arise from it. So we know today that Copernicus was right, and that the nightly motion of the night sky, the diurnal motion, is due to the Earth's rotation about its own axis. But with this new view of our solar system, we have a couple definitions of day. So the most common one that we know of is the solar day. That is the amount of time it takes the sun to return to the same point in the sky. So we can think of that as how long it takes for the sun to rise again after one day. But after each solar day, the stars in the celestial sphere are not exactly in their previous location. And this is because the Earth is simultaneously orbiting around the sun as well as spinning about its own axis. So the amount of time that it takes the Earth to rotate about its axis is actually slightly less than the amount of time it takes the sun to return to the same spot in the sky. So the time that it takes the Earth to rotate about its axis is what we call the sidereal day. And the time that it takes the sun to return to the same point in the sky is the solar day. These are very close in time, but the solar day is a little bit longer than the sidereal day. Another consequence of the heliocentric model is that we can now explain our seasons. So seasons are due to the Earth's simultaneous orbit around the sun and its rotation on an inclined axis. The Earth does not spin perfectly, but kind of has a little bit of wobble around it. And so as it orbits around the sun, the tilt of the Earth's axis causes different parts of the Earth to experience longer and shorter days and get more and less sunlight. The annual winter and summer solstices occur in the northern hemisphere when the Earth is at the highest and the lowest points in its orbit. So the winter is when it is at the highest point, and the summer solstice is when it is at the lowest point in its orbit. This inclined orbit is also why the amount of daylight is shortest on the winter solstice and longest on the summer solstice. And then we also have the vernal and autumnal equinoxes. They are points where the Earth is inclined such that the day and night hours are equal. So when we have the longest day of the year is the summer solstice, the shortest day of the year is the winter solstice, and then the vernal and autumnal equinoxes are when day and night have equal length. Another consequence of the heliocentric model is the phases of the moon. So the Earth is orbited by the moon, but the moon does not emit its own light. The moon only reflects the light from the sun, from its surface, onto us. So the moon orbits the Earth once every 27.3 days, or that's one sidereal month. And during this revolution, it experiences different percentages of its surface reflecting the sun's light back to Earth. And so this is what we know as the lunar phases, how it goes through these 8 distinct phases of new moon, waxing crescent, first quarter, waxing gibbous, full moon, then waning gibbous, then third quarter, then waning crescent, and then we're back at new moon again. There is another consequence of the heliocentric model, and that is that the sidereal month, the time it takes for the moon to make one revolution around the Earth, is actually 2.2 days less than the full lunar cycle. That is, it's shorter than the time it takes the new moon to go through all of its phases back to new moon again. And this is because the Earth is simultaneously revolving around the sun while the moon revolves around the Earth. So the moon's phases are dependent on the sun's location in the celestial sphere. And this is why the sidereal month is shorter than the time it takes for a full lunar phase cycle. The last consequence of the heliocentric model that we're going to discuss are the phenomenon known as eclipses. So eclipses are rare, pretty rare events that occur due to the relative motions of the moon around the Earth and the Earth around the sun. So a lunar eclipse is when the moon enters the Earth's shadow, or it's behind the Earth with respect to the sun. And then a solar eclipse is when the moon passes between the Earth and the sun and it blocks out the sun's light. And a solar eclipse, actually, any eclipse can be total if the body in question is completely obscured. So if the moon is completely within the Earth's shadow, it is a total lunar eclipse. And if the sun is completely covered by the moon, it is a total solar eclipse. But the scale and angle and location of these phenomena are affected by the orbital complexities of the Earth and the moon and the sun. And so sometimes the moon can be a little bit further away and it doesn't completely cover the sun. So you can still see a little bit of a ring around of the sun's light around the moon, and this is referred to as an annular solar eclipse. So this brings us to the end of Lecture 2.